So far, we focused most of our attention on the algebraic and numerical aspects of exponential functions. We're now going to turn our attention to the graphs of these functions, your favorite part of this course. I was being a little sarcastic there, if you couldn't tell. Now, let's summarize this, okay? The domain of all exponential functions will be all real numbers. Range will be 0 to infinity. It will be continuous. There's no symmetry. It'll be bounded below. Remember, boundedness and the range go together. There's a boundary on the bottom part of the range, so that's why it's bounded below. There are no local extrema, so no mins and maxes. There's going to be a horizontal asymptote at y equals 0, no vertical asymptotes. If b is greater than 1, it's an increasing function. If it's between 0 and 1, it'll be a decreasing function. Okay? So you should be able to pick out the limits from there also. All right? So we're going to go through this. Now, translations, reflections, stretches, rigs. So stuff we covered in section 1.6, okay, is going to take part here. Example 4. Describe how to graph, or how to transform the graph of f into the graph of g, given that f of x equals 2 to the x. Sketch the graphs by hand and support your answer with a grapher. Well, first things first, let's graph 2 to the x, right? What's 2 to the 0 power? 1. So when x is 0, 2 to the x would be 1. How about 2 to the first power? 2 to the second power, 4. 2 to the third power is 8. What about 2 to the negative first power? 2 to the negative first power would be 1/2. I'll throw that here. 2 to the negative second power would be half of that, or 1/4, and then 1/8. So our graph will look like this. And this is 2 to the x. Now, what does the x minus 1 do? Remember, it's with the x. What does this do? What does that do to it? Does the minus 1 move it left, move it right, move it up, move it down? What do you guys think? Right. Okay, it's going to move. Remember, when it's with the x, it's going to go opposite. So it's going to shift 2 to the x to the right 1. You're shifting the graph of 2 to the x to the right 1. Okay? So all these points, I'm going to start here, it's going to move to the right 1. Now, it did say support it with your grapher. So 2 to the x and 2 to the x minus 1. Now, this window that we have -5 to 5 and -2 to 8. What's that?
Wouldn't know how you move it down 1 and see on the straight line going up and down, wouldn't that be a 0? You want to move it down 1/2?
Okay, I took all these points in blue,
yeah,
and I moved it to the right 1.
Oh, okay.
Okay, that's what I did. All right. So we graph this. Well, let me do one thing first. So here's 2 to the x, and here is 2 to the x minus 1. Okay? So that's what we have there. Now, again, let's graph 2 to the x. You should be able to graph that pretty quickly, I would hope, by now. Now, what does this do? Okay. It's either a reflection of the x or the y. This one will be a reflection of the y-axis because the x is turning to be negative. So we're going to reflect 2 to the x over the y-axis. Okay? Now, 2 to the 0 would still be at 1. 2 to the first power would really be 2 to the negative first power in our graph. So when x is 1, we'll be here. When x is 2, we'll be here. Now, when x is negative 1, 2 to the negative first will really be the value of 2 to the first power, so that's why we're here. And then we'll be here and here. That'd be 2 to the negative x. Okay. Are there any questions on A or B at this time? Let's look at C. Again, graph 2 to the x. What does this 3 do to it? This is going to be a stretch. Which way is it going to stretch? Is it going to stretch horizontally or stretch vertically? This is going to stretch vertically because it's outside the function, right? So, vertically stretch 2 to the x by a factor of 3. So basically all this is saying is take all your y values, multiply them by 3. 1 times 3 is 3, so I'll have a point here. 2 times 3 is 6. 3 times 4 is 12, so it's going to be like way up here. We're not going to worry about that one, so we'll put it on our graph. Half times 3 will be 3 halves. A fourth times 3 will be about 3/4. And then an eighth times 3 will be about 3/8, will be about there. Now again, these are just sketches, so they don't need to be perfect, but I do want to see some points on the graph. All right, so the natural base E. Natural base E. What is the domain? Selena, what's the domain? What's that? So how else can I write that? Instead of all real numbers, I could also write it out. Negative thing to infinity. Lydia, how about the range? Am I including 0? No. Well, is this thing continuous or not continuous? It is continuous. Now, do I have to write on its domain here?
No.
Do I have to write on its domain? No. The only time you remember you have to write continuous on its domain is when the domain is funny looking. This one says negative thing to infinity, so we don't have to worry about that. How about increasing or decreasing, Lash? What do you think?
Well,
It's always increasing, right? So it'll be negative thing to infinity. Kyrie, how about symmetry? No symmetry. Michael, boundedness?
bounded below.
Excuse me? Michael's turn?
Would you the
Michael,
alternative ones? Zero.
look here, what's it say? Bounded below, right? That's your next answer, good. Okay, so it is bounded below. Mitchell, any extrema? No, none. Carl, any asymptotes?
Horizontal.
Oh, 0.
Oh, that's so
Just 0?
That's embarrassing.
Oh,
Just 0?
my God.
Yes.
So no y equals or x equals 0, just 0?
Oh, y equals 0.
Thank you.
Number Carl?
Now,
Give me a break. I asked a lot of questions.
as x approaches negative infinity, As x approaches negative infinity, what is y approaching? 0.
Sure, just
As x approaches positive infinity, as x approaches positive infinity, y approaches positive infinity. Okay? Now again, because f of x is increasing, it's an exponential growth function, so e has to be greater than 0. But really, what is e and what makes it the exponential function? That's why we call it the exponential function. Now, the letter e is the initial last name of Leonard Euler, who introduced the notation. Because f of x equals e to the x has special calculus properties, e is the natural base of the exponential functions for calculus purposes. Now, if you look at your calculator, and right here is our natural log button, right? Right next to the 4. What's above the natural log button?
S.
Here's e to the x, okay? And then if we go right next to it, it's natural log, okay? Natural log and e are inverses of each other. That's why they're like that on the calculator, okay? Now, we can't compute the irrational number directly, but if we use this formula, the limit as x approaches infinity of 1 plus 1 over x to the x power. So if we figure out 1 plus 1 over x to the x power, then we'll be able to see what's going to happen here. This 7 here actually should be an 8 when we get to it. Okay? But if you put 1 into here, you'll end up getting 2 as an answer. Okay? If you put 10 in, you'll get 2.5. If you put 100 in, you'll get 2.70. If you put 1,000 in, you get 2.716. If you put 10,000 in, 2.7181. If you put 100,000 in, 2.71826. It's going to keep going on and on and on. If you put e to the first power into your calculator, you'll get this. 2.718281828, all 459 is eventually what's going to happen. Okay? It's going to keep getting bigger and bigger like that. Now, usually, we're more interested in the exponential function and variations of this function than in the irrational number e. In fact, any exponential function can be expressed in terms of the natural base e, which is something we're going to be going over a little bit later in this chapter. Okay? Now, here's the theorem. Exponential function, the base e. Any exponential function, a times b to the x, can be written as f of x equals a times e to the kx for an appropriately chosen real number constant k. If a and k are both greater than 0, then it's an exponential growth function. If a is greater than 0 but k is less than 0, it's an exponential decay function. Okay? So here's exponential growth, here's exponential decay. In section 3.3, we're going to develop some mathematics so that for any positive number, we can easily find the value of k such that e times k to the x equals b to the x. In the meantime, we're just going to worry about it graphically. Okay? So let's look at example 5. Describe how to transform the graph of f of x equals e to the x into the graph of g. Sketch the graphs by hand and support your answer with the grapher. Now, we know e to the first power is 2.710. Let's, where's that quick? If we put e to the x in here, and we found the table, okay? You could really see, this is all we'll be able to fit on our graph, right? When x is negative 4, it's like 0.018. When x is negative 3, it's like 0.05. And it soon gets bigger. Again, when x is 0, the value is going to be 1. So we'll have a graph here. 1 and 2.7, 2 and 7.4. And it gets real small real quick. When x is negative 1, it's negative 0.4. Here's e to the x. Now, what is that doing? What is that doing? It's going to be a stretch or a shrink, right? But is it going to be horizontal or going to be vertical? Because it's with the x, it's actually going to be horizontal, okay, not vertical. Now, to get you guys a better idea, let's actually put this in here. E to the 2x. Okay, what do you notice around here? Well, it's a little bit below, and then it's going to jump up real quick. Well, if we look at these here, it's still going to have the same initial value, right? 0, 1. But what do you notice when x is 1 here? What do you notice about the value here? Okay, this actually got bumped this way. Now, I'm willing to bet that the value when x is 1/2 will be 2.718, okay? So everything got horizontally shrunk by a factor of 1/2. So this will be a horizontal okay? So there's my horizontal shrink. So what's going to happen? We're going to come here. And here's E with 2x. Okay. Are there any questions on example 5a, what we have to do? Okay. Now, if we look at example 5b, what is this? Where is this going to reflect? X-axis or y-axis? This will reflect on the y-axis, okay? So it'll look just like the previous example. What's C going to do? What is C going to do? It's going to be vertical stretch by a factor of 3. So we're going to multiply all of our y values by 3. Okay? So this will reflect e to the x over y-axis, and we don't have time to draw it, so we'll just worry about that later. This will be vertically stretch e to the x by a factor of 3. Okay. Are there any quick questions over example 5 at this time?